Okay, so we're back with part 2 of chapter 7, the input and output, and here we're going to talk about techniques for dealing with input and output. The first of these is programmed I/O, and this is the oldest and probably the most straightforward of the three techniques. So let's take a look at it here. So the processor executes instructions related to I/O by issuing a command to the appropriate I/O module. It then waits until the I/O module performs a requested action and then sets the appropriate bits in the I/O status register. The I/O module doesn't alert or interrupt the processor, and the processor will periodically check the status of the I/O module until it finds that it's complete. So here's the flow chart for it. Issue read command to I/O module, read the status of the I/O module. If it's not ready, go back and issue the read commands. If there's an error condition, proceed with an error handler. If it's ready, read word from the I/O module, write word into memory, and if you're done, go on to the next instruction. Otherwise, continue to issue those read commands, and that's kind of the overview of the whole. So different commands, control is used to activate the peripheral and tell it what to do. Test is used to test various status conditions. Is it powered on? Is it available for use? Have we completed our operation already? Read causes the I/O module to obtain an item of data from the peripheral and place it in an internal buffer, so getting input. Write causes the I/O module to take an item of data from the data bus and transmit that data item to the peripheral. For example, display a character on the screen. There's a close correspondence between the I/O instructions in memory and what the processor sends to the I/O module, usually a one-to-one correspondence. And typically there are a lot of I/O devices. Each device has its own address, and the command that we send it will contain that address so we know what we're sending. When the processor, main memory, and I/O share a common bus, there are two ways of dealing with the addressing. One of them is memory mapped I/O, which is there's a single address space for memory locations and I/O devices. They're all one big happy family. The processor treats the status and data registers of the I/O modules as memory locations themselves and uses the same machine instructions to access both memory and I/O devices. So we only need a single read and a single write line on the bus. An alternative is isolated I/O, where the bus can be equipped with a memory read and write, plus input and output command lines. The command line specifies whether the address refers to a memory location or an I/O device. And so the full range of addresses can be available for both. With 10 address lines, the system can support up to 1,024 memory locations and 1,024 I/O addresses. Because the address space for I/O is isolated from that of memory, it's referred to as isolated I/O. So again, the command line will specify whether we're referring to memory location or I/O device, and we can have the same size address space for either. So memory mapped has a larger number of instructions, and an advantage of memory mapped is that there's a large repertoire of instructions that can be used a lot for more efficient programming. Disadvantages that we use up valuable memory space that is used to refer to the addresses of I/O devices. Programmed I/O also has drawbacks. Processor has to wait a long time for the I/O module of concern to be ready for either reception or transmission of data, and while waiting, it has to periodically interrogate the status of the I/O module. Hey, are you done yet? As a result, the performance of the entire system gets degraded. You saw that with earlier generations of computers where it would degrade rapidly as you were trying to print something. That gave rise to an idea called interrupt-driven I/O, where we put in an interrupt cycle within that fetch, decode, and execute command cycle. So this alternative, the processor issues an I/O command to a module and then goes and does some other useful work besides querying the I/O module as to whether it's done or not. The I/O module will control it and then interrupt the processor to request service when it's ready to exchange data again with the processor. Processor executes the data transfer as before and then resumes its former processing. So how does this work? So the device issues an interrupt signal to the processor. The processor finishes execution of the current instruction whatever it was doing. If it was an addition, movement of memory, it finishes that up before responding to the interrupt. It then tests for an interrupt, determine that there is one, sends an acknowledgement signal to the device that issued the interrupt, and that's step 3 there in the hardware. Next, it pushes the program status word and the program counter onto the control stack, because it needs to transfer control to the interrupt routine. So it needs to save where it's at before it goes about dealing with that interrupt. So what is it I'm doing? I'm going to put that aside, write it down in that program status word and the program counter in my stack so that I know what the next instruction to be executed was, what I was doing before I was interrupted. Processor now loads the program counter with the entry location of the interrupt handling program that'll respond to this interrupt. And at this point, the program counter and program status word relating to the interrupted program have been saved onto the stack. There's other information that's considered part of the state of the executing program. In particular, contents of the processor registers need to be saved because these can be maybe used by the interrupt handler, and we wouldn't want to lose track of the things that we're adding or accumulating in our previous program. So we have to save that out as well. And then the contents of all registers plus the address of the next instruction get pushed onto that stack for saving where we were. The interrupt handler processes the interrupt, and this includes an examination of the status information relating to the IO operation or any other event that caused the interrupt. It could have been an error, but typically it's IO. When interrupt processing is complete, the saved register values are retrieved from the stack and we restore back to where we were. And then restore that program's status word and program counter back on from the stack, and then the next instruction to be executed from the previously interrupted program gets executed because we're back to where we were. So we basically keep track of where we're at when we're interrupted, write all that down, and then go ahead and deal with the interrupt, and then put all that back into the processor, and then continue on our merry way with the program. A couple of design issues for interrupt processing, because there will be multiple IO modules. How does the processor determine which device issued the interrupt? And if multiple interrupts have occurred, how does it decide which one to process? So for device identification, we can have multiple interrupt lines, basically between the processor and the IO modules. This is the most straightforward approach to the problem. And even if multiple lines are used, it's likely each line will have multiple IO modules attached to it. Another way is doing a software pull. When it detects an interrupt, it branches to an interrupt service routine whose job is to ask each IO module, which one of you caused the interrupt? Because we're doing that in software, it's a bit more time consuming. So we could look at doing a hardware pull through a daisy chain. And there are two approaches, the hardware pull and the vectored. The vectored is where the address of the IO module or some unique identifier is stored. And the processor uses this vector as a pointer to the appropriate service routine. So we don't need to execute a general interrupt routine first. The other one is bus arbitration, where an IO module needs to gain control of the bus before it can raise the interrupt request line. When the processor detects the interrupt, it responds on the interrupt acknowledge line. Then the requesting module places its vector on the data lines. Multiple interrupts, again, if you have more than one interrupt at a time, how do you deal with it? You can assign priorities to them. One is multiple lines, where the processor just picks the interrupt line with the highest priority. Software pulling, the order in which the modules are pulled determines their priority. Daisy chain, similar, that's the hardware approach. The order of modules on the daisy chain determines their priority. And bus arbitration employs a priority scheme. And we talked about that in section 3.4 of the text. So thanks so much for watching.